Hello everyone, thank you for attending this talk. My name is Amir Tag and I'll be presenting a 3D printed hexagonal cylinder Leaky-Wave antenna from the directional coverage. First, I will start with an introduction and then I will do like the analysis of the unit cell that I'm employing for the Leaky-Wave antenna. And then we're going to present some results about this hexagonal Leaky-Wave antenna and then we'll conclude. Leaky-wave antennas are a traveling type wave of antenna, which are valued for their beam scanning capability and their frequency agility, and they enable actually the controlled leakage of electromagnetic wave throughout the structure, where the beam scanning depends on the frequency. So 3D printing allows for a rapid prototyping that for complex geometry that traditional PCB cannot achieve. For example, in our case, the hexagonal type of shape cannot be achieved with a traditional PCB methods. Um, so the existing Leaky-Wave antennas that are on the literature, they focus on like directional scanning. And here we want to address the fact that we can achieve full 360 degrees azimuthal coverage and also a wide elevation scanning using this novel hexagonal cylinder configuration, where the goal would be to design and simulate a 3D printed hexagonal liquid antenna structure that can achieve omnidirectional coverage by through frequency scanning as well as um, port switching with high gain and efficiency. So, for our liquid antenna, we're gonna employ the following unit cell. You can see the circular patch unit cell. Um, so we're going to design actually a 1D periodic liquid antenna by cascading these unit cells. And the material used for this unit cell is Inc 1092 dielectric substrate, which has a relative permittivity of around 3.2 and at the working frequency. And the conductor is actually silver nanopractical traces. And actually, we employ this type of unit cells because it actually offers a lower Q factor, which means we're going to have a broader bandwidth and improve radiation efficiency in this case. From the Bloch-Brouwer theory, we can extract the dispersion diagram of the unit cell by first calculating its S parameters, and then from there we can convert the S parameters to an ABCD matrix. And from the ABCD matrix, we can extract the phase constant and the attenuation constant of the unit cell. So the normalized phase constant is depicted in red, the dashed red line, and the attenuation constant is the dashed green line. So what this tells us is that um, we compare them relative to the light line, and so when the phase constant is below the light line, that means we are dealing with a radiation of our liquid antenna. Else, when it's above this light line, so it's a bound mode, so it does not radiate. We can see that the radiation in this case starts at around 19 gigahertz. And what the dispersion diagram also tells us is that we can see that at around 28 gigahertz we are at the broad side because the phase constant is equal to zero, which means we are at a 0 degree broadside radiation. And what usually happens at broadside is that we have more attenuation we can actually predict that from the Kramers-Kronig relations. Um, and when the slope is negative, at the broad when the phase constant slope is negative, that means we are dealing with backward radiation of our liquid antenna. Else, when it's positive, we are at a forward radiation. So the radiation direction is actually controlled by the phase constant, and we can see that as the frequency varies, then the beam direction will change, which is characteristic of the Leaky-Wave antenna. And we can see that at broadside, you have a little bump of the attenuation, but it is minimum. And we actually simulated many unit cells, and we found that actually the circular patch geometry, which was the one that fitted best um, our application. So now that we have analyzed the unit cell dispersion diagram, we can actually take this unit cell that of the previous figure and actually cascade them in this manner. And now we have a full Leaky-Wave antenna with 15 unit cells. And we're going to verify its scanning performance. So these are the beam scanning results of our Leaky-Wave antenna, where we can clearly see that as we vary the frequency, the beam direction changes. And actually, this beam scanning result, they agree well with the dispersion diagram that we have presented earlier, where we can see that the broadside at 20 is indeed at 20 gigahertz. So you see this here we are at 0 degrees, which is clear at 28 gigahertz. And we can see that actually the gain of the beam drops as we increase the frequency, which is again predicted by the dispersion diagram, where it can be seen that the attenuation increases as we increase the frequency. And we can see that over the whole frequency range, the gain of the gain is over 12 dBi, 12 dBi, and we actually have a pretty narrow beam width. Where the average beam width, half power beam width, is about 10 degrees, and the beam scanning is actually from 62, minus 62 to 35 degrees in the theta direction. We can see these are the S parameter results of our 1D periodic Leaky-Wave antenna. We have traced the S21 and the S11. So we can see that again, this agrees well with the dispersion diagram, where we can see that there's a slight mismatch at broadside at 28 gigahertz due to the bright reflections, and we can see that indeed over the frequency band there is a good match of our antenna, which increases as the frequency goes up, which is predicted by the attenuation constant. And yeah, so the S21 is about minus 5 dB over the frequency range, but drops as we move upwards in frequency. Now we will move on to the hexagonal Leaky-Wave antenna. It is made by taking the previous Leaky-Wave antenna and putting it into this hexagonal shape. Uh, and so we have 6 ports for this hexagonal Leaky-Wave antenna, where each Leaky-Wave antenna presents 1 port, and the other side would be terminated by a 50 ohm load. So each phase is terminated by a 50 ohm load. Um, so in this manner, we can actually excite each face of the hexagon in order to achieve full azimuthal scanning, and we will present the results. So these are the results of our hexagonal uh, Leaky-Wave antenna, where so when we excite port 1 through port 6, you can clearly see that the beam in the azimuthal direction changes direction to achieve a full 360 degrees scanning, where the beam width is actually 133 degrees, and so the scanning step is about 60 degrees, and you can see in this manner we can achieve a full 360 degrees omnidirectional coverage. So this axis represents the gain of our antenna, and what is around this the circumference of the plot of the polar plot is is the angle, the azimuthal angle, and we can clearly see that the average gain at each the gain is consistent when we switch between each port, and it maintains a gain of around 15.2 dBi. And we actually can see there's we have minimal side lobes of this antenna here, and it operates across the frequency band of 20 to 40 gigahertz, but here we only have the radiation pattern at 20 gigahertz. So actually, in the original Leaky-Wave antenna, where if we only have one face of the Leaky-Wave antenna, the half power bandwidth is 120 degrees. But when we actually excite this hexagonal face, it increases to 133 degrees. And this is actually due to the electromagnetic coupling between the adjacent faces of the hexagon, which slightly broadens the elevation beamwidth. So as a conclusion, so the antenna that we have designed actually, so it was done on a 3D printed manner, and it actually can achieve a 360 degrees scanning by switching between the port of each face of the hexagon, and about 100 degrees elevation scanning by uh, taking the frequency scanning of the Leaky-Wave antenna. Eh, so this antenna actually demonstrates like a pretty high gain with more than 12 dBi and a wide bandwidth of 20 gigahertz, but we have a slight degradation at broadside and a radiation efficiency of 68.5%, which is acceptable for Leaky-Wave antenna. And we have it can be used for many applications such as wireless communications, where we can be using on the base station, or radar for uh, maybe scanning, radar scanning, robotics also for spatial scanning, and sensor networks. Thank you very much for your attention.